Okay, I'm going to talk about the three different types of symmetry that we're going to deal with in geometry. And the first one are the lines of symmetry. So we can be symmetric about a line. We know that that would be a line of reflection like we constructed a couple days ago. So the line of symmetry we know is equidistant from all the corresponding pairs of points. So if we think of an image, like let's take this isosceles triangle, that image is really a reflection of half the triangle over a line of symmetry, because when you reflect it, you get the other side. So if I were to draw in or sketch in the line of symmetry here, it's going to be right down the middle. And you know, if you fold this over this line, if you fold this half over this line of symmetry, it's going to match up with the other half. A rectangle has two lines of symmetry. I think I'll dot it in like that. You can fold it across the long side, you can fold it across the short side, and the two sides would match. Now the next shape, this is a hexagon, a six-sided figure. Because it has an even number of sides, I can draw lines of symmetry that bisect the sides and also bisect the angles. So I've got several lines of symmetry here. In fact, there's going to be 6 different ones. So if I bisect all the sides, I have 1, 2, 3 lines of symmetry. And then if I bisect all the angles, I've got 4, 5, 6. So that looks a little nutty there. If I make these more solid, I don't know if that will help. I really need a straight edge to do this. But we have 6 lines of symmetry, bisecting the angles and bisecting the sides. Okay, that's a little crazy. But the next one, if you look at it, I don't have any lines of symmetry with this guy because I can't fold him anywhere and have the sides meet. Now some kids might say if you go corner to corner, but if I did that and folded this corner up, he would end up here and he wouldn't match up with that corner. So that guy has no lines of symmetry. What he does have is something called rotational symmetry, which is what we're going to talk about next. So we're going to talk about rotational symmetry next. Rotational symmetry is a rotation that maps a figure back onto itself. So when we rotate a figure, we're not rotating about a separate point. We're rotating about a point in the center of the figure, like in the triangle down here. And if I have a figure that has rotational symmetry, I can turn this figure, and within a certain number of degrees before 360, before a complete rotation, it's going to look like the original figure. Regular polygons, that's which all sides and angles are congruent. In regular polygons, the number of rotational symmetries is equal to the number of the sides of the figure, which means for the triangle I have 3 rotational symmetries because I can take this top point and rotate it here, and then rotate it here, and then rotate it here, and the figure will map to itself. So to figure that out, if I want to figure out the actual degree measure of rotation, which would be if you look in this, if you take the center and draw lines to the vertices, this angle measurement in here is going to be the angle of rotation. How much do I have to rotate this image before it looks like itself again? And you basically take the number of sides and you divide it into 360. So 360 divided by 3 is 120 degrees. A triangle takes 120 degrees before it looks like itself again. So if you look at a square has 4 sides, so if you divide 360 by 4, you're going to get 90 degrees. So a square has a 90 degree of rotation. A pentagon has 5 sides, so 360 divided by 5 is 72 degrees. And then a hexagon would be 360 divided by 6 is going to be 60 degrees. That's how you find the degree of rotation. That's how much it takes before an image will map back onto itself. Now, a rotation of 360 degrees is called the identity transformation because nothing really changed. If I labeled each vertex A, B, C, D, E, and F and rotated it 360 degrees, these letters would all be in the same place again. That's why it's called the identity transformation. Point symmetry is a subset of rotational symmetry. Point symmetry is defined as when you reflect an object through a point, the image creates point symmetry, which means the object will look exactly the same upside down. So basically, point symmetry is the fact that if you rotate an object 180 degrees, so if you turn your paper upside down and the image looks like the original, that image will have point symmetry. So if I look at my examples down here, I've got a parallelogram, and if you rotate this 180 degrees, it's going to look like the same parallelogram. So this one has point symmetry. The pentagon does not, though, because if I rotate him 180 degrees, he's going to be pointing down instead of up, so he's a no. Any even-sided figure, 1, 2, 3, 4, like this has 8 pieces to it. If you rotate this 180 degrees, it's going to look like itself. And then playing cards are typically designed to have point symmetry. So if you turn the card upside down, he's going to look like himself. So here's a typical question that you might be asked in regards to all these different types of symmetry. We have a pentagon, A, B, C, D, E, and we want to draw all the lines of symmetry first. So in a pentagon, if I think about line symmetry, I can go through each of the vertices, since it's a regular pentagon, and all of those lines create an image that I can fold on the line and the sides would match. But I also have D, I forgot a couple, and C. So you've got 5 lines of symmetry. And then the center of the rotational symmetry is where those 5 line symmetries intersect. So that's in the center of the pentagon. So describe all the symmetries explicitly. What kinds are there? Well, we have line symmetry, because I just drew them all. And a pentagon is a regular polygon, so he's going to have rotational symmetry. But he's not going to have point symmetry. And he'll always have the identity symmetry. That means when you rotate it 360. So that's kind of a given. So he has line and he has rotational, but he does not have point symmetry because I can't rotate him 180 degrees and have him look like himself. How many are rotations? I can rotate my image 5 times because it's equal to the number of sides. And the angles of rotation would be 360 divided by 5, so that's 72 degrees. And then the number of reflections, I have 5 different reflections I can do. Because again, I have 5 different lines of reflection, 1, 2 for each of the points, because my image is symmetric about every line that goes through a vertex through the opposite side. So that's just a brief introduction to line and rotational and point symmetry. We're going to use that in class and start mapping different letters as we rotate around with these rotational symmetries and reflections, and we'll practice that when we get to class.